Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. The solar system often feels serene when viewed from afar, a graceful clockwork of planets circling the sun in predictable paths. Yet beneath this calm appearance lies a realm filled with danger, violence, and extremes. From colossal planets with crushing gravity to tiny fragments of rock traveling faster than rifle bullets, the solar system is home to some of the most dangerous objects known to science. These objects have shaped the history of planets, caused mass extinctions, and continue to pose potential threats to Earth and future space exploration. Understanding them not only reveals how our cosmic neighborhood works, but also reminds us how fragile life can be in a dynamic universe. Among the most infamous, dangerous objects in the solar system are asteroids. These rocky remnants of planet formation range in size from small boulders to bodies hundreds of kilometers wide. Most asteroids reside in the main asteroid belt between Mars and Jupiter, but their influence reaches far beyond that region. Over billions of years, gravitational interactions, especially with Jupiter, can disturb asteroid orbits, sending some of them inward toward the inner planets. When an asteroid crosses Earth's orbit, it becomes a near-Earth object, and some of these are classified as potentially hazardous. The danger of asteroids is not theoretical. Geological evidence shows that Earth has been struck many times in the past, sometimes with catastrophic consequences. The most famous example is the asteroid impact about 66 million years ago that contributed to the extinction of the dinosaurs. That object was likely around 10 kilometers wide, yet it released energy equivalent to billions of nuclear bombs. Smaller asteroids can still be devastating. A rock just a few hundred meters across could destroy a major city or trigger global climate effects if it struck land or ocean. Even much smaller objects, only tens of meters wide, can cause significant damage, as demonstrated by the Chelyabinsk meteor in 2013, which shattered windows and injured over 1,000 people in Russia, despite exploding high in the atmosphere. Asteroids are dangerous not only because of their size and speed, but also because they are difficult to detect. Many are dark, composed of carbon-rich material that reflects little sunlight. They can approach Earth from the direction of the sun, making them almost invisible to ground-based telescopes until they are very close. This uncertainty drives ongoing efforts to survey and track near-Earth objects, as well as research into planetary defense strategies such as deflection missions. Closely related to asteroids, comets represent another major hazard. Often described as dirty snowballs, comets are made of ice, dust, and rock. They originate from the cold outer regions of the solar system, primarily the Kuiper Belt beyond Neptune and the distant Oort cloud, a vast spherical reservoir of icy bodies extending far into interstellar space. When gravitational disturbances send a comet toward the inner solar system, it accelerates rapidly as it falls toward the sun, developing a glowing coma and long tail as its ices vaporize. Comets are especially dangerous because of their extreme velocities. While asteroids typically travel at tens of kilometers per second relative to Earth, comets can move much faster, sometimes exceeding 70 kilometers per second. The kinetic energy of an impact increases with the square velocity, meaning a cometary impact can be far more destructive than an asteroid of similar size. Additionally, long-period comets from the Oort cloud can appear with little warning, giving humanity very limited time to respond. Beyond impact threats, comets may also pose subtle dangers. As they pass through the inner solar system, they shed debris along their orbits. Earth encounters these debris streams as meteor showers. Most meteors burn up harmlessly, but occasionally larger fragments survive atmospheric entry. While individual meteoroids are usually small, the cumulative risk over time is not negligible. Moving outward from small bodies, we encounter the planets themselves, some of which are among the most dangerous objects in the solar system due to their extreme environments. Jupiter, the largest planet, is both a protector and a threat. Its immense gravity acts like a cosmic vacuum cleaner, deflecting or capturing many asteroids and comets that might otherwise head toward the inner solar system. At the same time, Jupiter's gravity can also destabilize orbits, flinging objects inward and increasing the number of potential impactors. Jupiter's role is complex, and without it, Earth's impact history might have been very different, though not necessarily safer. Jupiter is also dangerous to spacecraft and anything venturing close because of its intense radiation belts. These belts, formed by charged particles trapped in the planet's powerful magnetic field, are far more extreme than Earth's Van Allen belts. Radiation levels near Jupiter can damage electronics, degrade materials, and pose lethal risks to unprotected humans. Even robotic missions must be carefully shielded and designed to survive limited exposure. Saturn, famous for its beautiful rings, also presents hazards. While its radiation belts are weaker than Jupiter's, Saturn's complex system of moons, rings, and magnetic fields creates a dynamic and potentially dangerous environment. The rings themselves are composed of countless particles ranging from tiny ice grains to house-sized chunks. Traveling through or near the rings at orbital speeds would be fatal for a spacecraft or astronaut. Even Saturn's moons, such as Enceladus, with its geysers of water vapor and ice, present collision risks for orbiting probes. The terrestrial planets closer to Earth are not free of danger either. Venus, often called Earth's sister planet due to its similar size, is one of the most hostile worlds imaginable. Its thick atmosphere is composed mainly of carbon dioxide, or methane, creating a runaway greenhouse effect that raises surface temperatures to over 400 degrees Celsius, hot enough to melt lead. The atmospheric pressure at the surface is more than 90 times that of Earth, equivalent to being nearly a kilometer underwater. Clouds of sulfuric acid rain down through the atmosphere, evaporating before they reach the ground, but corroding anything exposed. Venus demonstrates how a planet can become a dangerous inferno through climate processes, offering a cautionary tale about atmospheric evolution. Mars appears more benign at first glance, but it also hides dangers. Its thin atmosphere offers little protection from solar radiation and cosmic rays, making the surface hazardous for long-term human exposure. Mars is also prone to global dust storms that can last for months, covering the planet and blocking sunlight. These storms can cripple solar-powered equipment and pose risks to explorers. Additionally, the low gravity and extreme cold present physiological challenges that could threaten human health. One of the most dangerous objects in the solar system is the Sun itself. As a star, the Sun is the ultimate source of energy for life on Earth, but it is also capable of immense destruction. Solar flares and coronal mass ejections can hurl billions of tons of charged particles into space at high speeds. When these particles interact with Earth's magnetic field, they can produce beautiful auroras, but strong solar storms can also disrupt satellites, damage power grids, interfere with communication systems, and endanger astronauts. The most extreme solar events are rare, but potentially devastating. A sufficiently powerful solar storm could knock out electrical infrastructure on a global scale, causing widespread technological disruption. Historical records and geological evidence suggest that the Sun is capable of producing events far more powerful than anything experienced in the modern technological era. In this sense, the Sun represents a constant, unpredictable hazard, one that humanity must learn to monitor and mitigate. Beyond the Sun, some of the solar system's most dangerous objects are its moons. Jupiter's moon Io is the most volcanically active body known, with hundreds of active volcanoes driven by intense tidal heating. Its surface is constantly reshaped by lava flows and sulfurous eruptions. While fascinating scientifically, Io is an extremely hostile environment. Any attempt to land there would face intense radiation, unstable terrain, and frequent volcanic activity. Europa, another of Jupiter's moons, is less obviously violent but still dangerous. Its surface is a shell of ice covering a global ocean beneath. The radiation environment around Europa is severe, and its icy crust is fractured and constantly shifting. Similar dangers exist on other icy moons, such as Enceladus around Saturn, where jets of water ice erupt into space. These plumes create hazards for spacecraft and demonstrate the dynamic, energetic nature of these worlds. The outer reaches of the solar system harbor dangers that are less immediate but no less significant. The Kuiper Belt and Oort cloud are vast reservoirs of objects that can be perturbed by passing stars or galactic tides. When this happens, Comets can be sent hurtling toward the inner solar system. These distant regions act like a loaded gun, quiet for long periods, but capable of unleashing sudden threats. Even seemingly empty space can be dangerous. Micrometeoroids, tiny particles often no larger than grains of sand, travel at extreme speeds. In space, even a speck of dust can punch a hole in metal or damage sensitive equipment. Spacecraft are constantly bombarded by these particles, and over time, the cumulative effect can be significant. For astronauts, exposure to micrometeoroids is a serious concern, requiring protective shielding and careful mission planning. Another often overlooked danger comes from gravitational interactions themselves. The solar system is a complex, interconnected system where small changes can have large consequences over long timescales. Orbital resonances can destabilize the paths of asteroids and comets, increasing impact risks. Even the orbits of planets are not perfectly fixed. Over millions of years, they can shift in subtle ways. While these processes are slow, they underscore that the solar system is not static but constantly evolving. Human activity introduces new dimensions of danger as well. Space debris, consisting of defunct satellites, fragments from collisions, and discarded rocket stages, now orbits Earth in large quantities. While not a natural object, this debris behaves like the dangerous objects of the solar system, traveling at high speeds and capable of destroying operational satellites or threatening crewed missions. As humanity expands its presence in space, managing this artificial hazard becomes increasingly important. Despite these dangers, it is important to recognize that the solar system is not uniquely hostile. Many of the processes that create danger are also those that made life possible. Asteroid impacts may have delivered water and organic molecules to early Earth. The sun's energy drives climate and biological activity. Volcanism recycles nutrients and shapes planetary surfaces. Danger and creation are deeply intertwined in cosmic history. Studying the most dangerous objects in the solar system is therefore not just about fear or survival. It is about understanding our origins and our future. By learning how asteroids move, how the sun behaves, and how planetary environments evolve, we gain the ability to predict and potentially mitigate threats. Space missions that track near-Earth objects, monitor solar activity, and explore extreme worlds are investments in knowledge and safety. The solar system is a place of wonder and beauty, but it is also a realm of power beyond everyday human experience. From the silent menace of a dark asteroid to the roaring fury of a solar storm, the dangers are real and ever-present. Yet humanity has already taken its first steps toward awareness and preparedness. With continued exploration, observation, and cooperation, the most dangerous objects in the solar system can become not just sources of risk, but keys to deeper understanding of the universe we call home. Continuing our journey through the most dangerous objects in the solar system, it becomes clear that danger is not limited to dramatic collisions or violent explosions. Sometimes the most serious threats are slow, invisible, and relentless, acting over long periods rather than in sudden catastrophes. One such danger is radiation, a pervasive hazard that fills much of space and intensifies near certain objects. Radiation comes from multiple sources: the sun, planetary magnetic fields, and cosmic particles originating far beyond the solar system. While Earth is largely protected by its magnetic field and thick atmosphere, many other regions are bathed in levels of radiation that would be deadly to humans and destructive to technology. Near planets like Jupiter and Saturn, radiation becomes a defining environmental feature. Jupiter's magnetic field is the strongest of any planet, creating radiation belts that dwarf Earth's. These belts trap high-energy electrons and ions, forming zones where radiation levels can be thousands of times higher than what humans can safely tolerate. Spacecraft that venture into this environment experience gradual degradation of their electronics, even with heavy shielding. Over time, radiation flips bits in computer memory, damages sensors, and weakens structural materials. Any future human mission to the Jovian system would face enormous challenges simply surviving the radiation long enough to conduct meaningful exploration. Saturn's radiation belts are less intense but still significant, especially when combined with the hazards posed by its rings and moons. The interaction between charged particles, magnetic fields, and icy debris creates a complex and unpredictable environment. Even Uranus and Neptune, though distant and less explored, possess magnetic fields that are strangely tilted and offset from their centers, producing radiation environments that change dramatically as the planets rotate. These unusual magnetic configurations make their surroundings potentially dangerous and difficult to predict. Another class of dangerous objects lies not in their immediate violence, but in their extreme physical properties. Neutron stars and black holes are not part of the solar system, but scaled-down analogs of extreme physics exist much closer to home. White dwarfs, for example, are the dense remnants of sun-like stars. While none orbit within our solar system, studying extreme density and gravity helps scientists understand why even smaller bodies can be dangerous. Some asteroids, known as rubble piles, are loosely held together by gravity. Interacting with them, whether by landing or attempting deflection, can cause them to fragment unpredictably, potentially increasing the danger rather than reducing it. Density and gravity also play a role in making planets dangerous. Mercury, the closest planet to the Sun, experiences extreme temperature variations, swinging from blistering heat during the day to freezing cold at night. Its proximity to the Sun exposes it to intense solar radiation and frequent bombardment by micrometeoroids. The lack of a substantial atmosphere means there is no protection from incoming debris. While Mercury's small size makes it less threatening to Earth, it is a reminder that proximity to powerful forces can turn even modest worlds into hostile places. Earth itself can be considered one of the most dangerous objects in the solar system, at least from a certain perspective. Our planet has active geology, a dynamic atmosphere, and powerful oceans. Earthquakes, volcanic eruptions, hurricanes, and tsunamis are driven by the same physical processes that make Earth habitable. Plate tectonics recycles carbon and nutrients, but it also generates devastating earthquakes and eruptions. Earth's atmosphere shields life from radiation, but it also enables powerful storms. In this sense, danger is not always external. Sometimes it emerges from the same systems that sustain life. Looking deeper into the solar system, we encounter another subtle but profound danger: gravitational tides. Tidal forces arise when gravity varies across an object, stretching and squeezing it. On Earth, tides are gentle, raising and lowering the oceans. But in other parts of the solar system, tidal forces can be extreme. Jupiter's moon Io is locked in a gravitational tug-of-war with Jupiter and neighboring moons, generating immense internal heat. This tidal heating powers Io's intense volcanism, making its surface one of the most unstable and dangerous landscapes known. Tidal forces can also tear objects apart. When a comet or asteroid ventures too close to a massive planet or the Sun, it can be ripped into fragments. This process creates families of debris that spread along similar orbits, increasing the likelihood of impacts elsewhere. A dramatic example occurred when comet Shoemaker Levy 9 was torn apart by Jupiter's gravity and then crashed into the planet in 1994. The impacts released energy equivalent to millions of megatons of TNT and left scars larger than Earth. While Jupiter absorbed the blows, similar events involving Earth would be catastrophic. The Sun's gravity can also play a destructive role. Objects that fall too close can be stretched, heated, and vaporized. Sun-grazing comets are often destroyed during close passes, but in the process, they release vast amounts of material and energy. The Sun's gravitational influence extends far beyond its visible surface, shaping the orbits of planets and small bodies alike. Over long timescales, subtle changes in the Sun's output and gravitational interactions can influence planetary climates and orbital stability. Another dangerous aspect of the solar system lies in chemical extremes. Some planetary atmospheres and surfaces contain substances that are highly toxic or corrosive. Venus's clouds of sulfuric acid are the most famous example, but they are not unique. Titan, Saturn's largest moon, has lakes and rivers of liquid methane and ethane. While fascinating from a scientific perspective, these hydrocarbons are hazardous to humans and indicate a chemistry utterly alien to Earth's biology. Breathing Titan's atmosphere would be impossible without protection, and exposure to its cryogenic temperatures would be lethal. Mars, while less chemically extreme, still poses dangers through perchlorate and fine dust, that could be harmful if inhaled or ingested. Long-term human presence on Mars would require careful management of these chemical hazards. Even the moon, often thought of as relatively safe, has sharp, abrasive dust that can damage equipment and irritate lungs. This lunar dust, formed by billions of years of micrometeoroid impacts, clings electrostatically to surfaces and poses a serious challenge for sustained exploration. Time itself is an often underestimated factor in solar system danger. Some threats operate on timescales far longer than a human lifetime, making them easy to ignore. Orbital chaos, though subtle, can accumulate over millions or billions of years. Computer simulations suggest that the inner solar system may be only marginally stable over very long periods. While catastrophic changes are unlikely in the near future, the possibility reminds us that planetary systems are dynamic, not eternal. The distant future of the solar system also holds dangers tied to the evolution of the sun. As the sun ages, it will gradually become brighter, increasing the energy Earth receives. Over hundreds of millions of years, this could trigger a runaway greenhouse effect, similar to what may have happened on Venus. Eventually, billions of years from now, the sun will expand into a red giant, engulfing or scorching the inner planets. While this is far beyond any practical concern for humanity today, it underscores that even the most familiar object in the solar system will ultimately become deadly. Human exploration adds another layer to understanding danger. When spacecraft travel through space, they must navigate a gauntlet of hazards: radiation, temperature extremes, vacuum, micrometeoroids, and gravitational traps. A miscalculated trajectory can send a probe crashing into a planet or flinging off into deep space. Crewed missions amplify these risks, as human life is far less tolerant of error than machines. Every mission is a delicate balance between ambition and safety, shaped by the dangerous nature of the solar system. Yet, danger also drives innovation. The need to protect spacecraft from radiation leads to better materials and electronics. The threat of asteroid impacts inspires international cooperation in advanced detection systems. Studying solar storms improves our ability to protect power grids and communication networks on Earth. In confronting danger, humanity expands its technological and scientific capabilities. It is also worth considering perspective. The solar system may seem extraordinarily dangerous when viewed through the lens of human vulnerability, but on cosmic scales it is relatively calm. Compared to regions near supernovae, gamma-ray bursts, or the centers of galaxies, our neighborhood is fairly gentle. The dangers we face are manageable, given sufficient knowledge and preparation. This perspective highlights an important truth. Danger is relative, shaped by scale, context, and understanding. As we continue to explore and learn, the most dangerous objects in the solar system become less mysterious. Asteroids are mapped and tracked. Solar activity is monitored continuously. Planetary environments are studied in detail by orbiters, landers, and rovers. Each discovery reduces uncertainty, turning unknown threats into known challenges. While we may never eliminate danger entirely, we can learn to live with it, adapt to it, and even use it to deepen our understanding of the universe. In the end, the solar system is a place of contrasts. Beauty and danger coexist, often inseparably. The same forces that sculpt rings around Saturn also hurl debris at incredible speeds. The same sun that nourishes life can unleash storms capable of disrupting civilization. By studying the most dangerous objects in the solar system, we are not just cataloging threats. We are uncovering the fundamental processes that shape worlds and determine their fates. This knowledge is essential, not only for survival, but for appreciating the delicate balance that allows life to exist at all. As we push further into understanding danger within the solar system, it becomes clear that some of the most threatening objects are dangerous precisely because they challenge our intuition. These are not always massive or dramatic bodies, but objects whose behavior is unpredictable, whose interactions amplify risk, and whose effects cascade across space and time. Chaos, in this context, is itself a dangerous force. One such source of danger lies in orbital instability. While planetary orbits appear stable over human lifetimes, they are governed by complex gravitational interactions that can evolve slowly and unpredictably. Small nudges, accumulated over millions of years, can shift the paths of asteroids, comets, and even planets. Resonances, where orbital periods align in simple ratios, can pump energy into an object's motion, gradually increasing its eccentricity until it crosses the orbit of another body. Many of the near-Earth asteroids we observe today were once safely confined to the main asteroid belt, only to be destabilized by resonances with Jupiter or Mars. These resonances are invisible dangers, operating silently over vast timescales. Unlike a sudden impact, they give no warning signs that humans can easily perceive. Yet they are among the most important mechanisms shaping the solar system's long-term evolution. They ensure that the population of potentially hazardous objects is never static, but constantly replenished. Another subtle danger arises from fragmentation. When asteroids collide with one another, or when comets break apart under tidal forces or thermal stress, they create clouds of debris. While the original object may have been tracked and monitored, its fragments may not be. Each fragment becomes an independent threat, often too small to detect easily, but still capable of causing serious damage. Fragmentation complicates planetary defense, turning a single known hazard into a swarm of unknowns. Spacecraft designers are acutely aware of this danger. Even tiny fragments, only a few millimeters across, can strike with enough energy to puncture shielding or shatter instruments. In Earth orbit, fragmentation events can trigger cascading collisions, creating even more debris in a chain reaction known as the Kessler syndrome. While this is a human-made problem, it mirrors natural processes elsewhere in the solar system, where collisions breed further hazards. The inner solar system also contains thermal dangers that push materials to their limits. Close to the sun, temperatures soar to extremes that challenge both natural objects and human technology. Spacecraft operating near Mercury or attempting close solar observations must endure intense heat and radiation. Materials expand, contract, and weaken under these conditions, increasing the risk of failure. Even asteroids that pass close to the sun can crack and fragment as their surfaces heat unevenly, shedding material that continues on altered trajectories. Heat is only one side of the thermal coin. Extreme cold presents its own dangers. In the outer solar system, temperatures plunge so low that common gases freeze solid. Metals become brittle, lubricants fail, and chemical reactions slow almost to a halt. For natural objects, this cold preserves volatile materials that can become explosive when heated. For spacecraft, it demands careful thermal management to keep instruments functioning. Gravity, often thought of as a stabilizing force, can also become a trap. Gravitational wells around planets and moons are deep, and escaping them requires precise energy calculations. A small error can doom a mission, sending a spacecraft crashing into a planet or stranded in an unplanned orbit. Natural objects experience similar fates. Captured asteroids can become temporary moons, only to later escape or collide unpredictably. These transient relationships add another layer of complexity and danger to the solar system's dynamics. Some of the most extreme dangers arise where multiple hazards overlap. Consider Jupiter's inner moons, where intense radiation, strong gravity, and frequent impacts coexist. Or consider the region near the sun, where heat, radiation, and tidal forces combine. In these environments, danger is not additive but multiplicative. Each hazard amplifies the others, creating conditions far more hostile than any single factor alone. The concept of danger also extends beyond physical destruction to existential risk. Life on Earth depends on a narrow range of conditions. Changes in solar output, orbital parameters, or atmospheric composition can push the planet beyond habitable limits. Large asteroid impacts can trigger global climate shifts by injecting dust and aerosols into the atmosphere, blocking sunlight for years. Even without a single catastrophic event, a series of smaller impacts or volcanic eruptions could gradually alter climate in dangerous ways. Solar variability plays a key role here. While the sun is relatively stable, it is not constant. Over decades and centuries, its activity fluctuates. Over longer timescales, its luminosity slowly increases. These changes interact with Earth's climate system in complex ways. A powerful solar storm may not destroy the planet, but it can disrupt the technological systems upon which modern civilization depends. In this sense, the danger is not to life itself, but to the fragile infrastructure that supports billions of people. Looking outward again, the giant planets influence danger through their migrations in the early solar system. Evidence suggests that Jupiter and Saturn shifted their orbits during the system's youth, scattering asteroids and comets throughout the inner regions. This period of heavy bombardment may have shaped the surfaces of all the terrestrial planets. While this era is long past, it reminds us that planetary systems can undergo dramatic rearrangements, transforming safe zones into dangerous ones. Even today, passing stars can influence the solar system's outskirts. A star drifting too close can disturb the Oort cloud, sending a shower of comets toward the inner planets over millions of years. Such events are rare, but on geological timescales, they are inevitable. When they occur, the risk of impacts increases significantly, creating periods of heightened danger. Psychologically, danger in the solar system challenges human perception. We evolved to respond to immediate threats, not slow-building risks unfolding over thousands or millions of years. This makes it difficult to prioritize planetary defense or long-term monitoring of solar activity. Yet understanding danger requires expanding our sense of time and scale, learning to think beyond individual lifetimes. Despite all these hazards, it is important to emphasize that danger does not imply doom. The solar system has remained stable enough for life to arise and persist for billions of years. Earth has survived countless impacts, climate shifts, and solar storms. The fact that we are here to study these dangers is evidence of resilience. But resilience does not mean invulnerability. The future of human exploration will depend on how well we understand and manage these risks. Missions to asteroids may one day test deflection technologies. Lunar bases will need protection from radiation and micrometeoroids. Journeys to Mars must contend with long-term exposure to cosmic rays and the psychological strain of isolation. Each step outward requires a deeper appreciation of the solar system's dangerous nature. Education plays a crucial role in this process. By communicating these dangers clearly and accurately, scientists help society make informed decisions. The goal is not to inspire fear, but respect. Respect for the power of natural forces, for the complexity of cosmic systems, and for the limits of human technology. Ultimately, the most dangerous objects in the solar system are dangerous because they remind us of our place in the universe. We are not separate from cosmic processes. We are embedded within them. Asteroids, comets, planets, and the sun itself are part of a vast interconnected system that shapes our past and future. By studying these objects, we learn not only how the solar system works, but how to survive and thrive within it. As our knowledge grows, danger becomes less of an unknown enemy and more of a challenge to be met. The solar system will never be completely safe, but it does not need to be. With understanding, preparation, and curiosity, humanity can navigate its hazards and continue exploring the extraordinary environment that surrounds our small, fragile world. Another category of danger within the solar system lies in energy stored beneath planetary surfaces. Internal heat, whether generated by radioactive decay, tidal friction, or residual heat from formation, can be released suddenly and violently. Volcanic eruptions are the most obvious expression of this energy, but they are not limited to lava flowing gently across a surface. On bodies like Io, eruptions eject material hundreds of kilometers into space. These eruptions reshape the surface constantly and fill surrounding space with charged particles and debris, creating an environment hostile to both natural stability and artificial exploration. Cryovolcanism represents a different but equally dangerous expression of internal energy. On icy moons such as Enceladus, Triton, and possibly Pluto, eruptions involve water, ammonia, or methane instead of molten rock. These substances erupt explosively in the vacuum of space, freezing instantly into sharp ice particles that travel at high speeds. While beautiful when observed from afar, such environments pose real hazards for spacecraft flying through plumes or orbiting nearby. A collision with fast-moving ice grains can damage instruments and compromise missions. Internal energy also drives tectonic activity. While Earth's plate tectonics are relatively well understood, other bodies may experience tectonic processes that are far less predictable. Fracturing of icy crusts, surface collapses, and sudden shifts can occur without warning. These processes remind us that danger does not always come from above. It can emerge from within a world itself. Electromagnetic danger is another underappreciated aspect of the solar system. Magnetic fields interact with solar wind in complex ways, generating electric currents and radiation. Around planets with strong magnetic fields, this interaction can produce intense auroras, but also powerful electromagnetic disturbances. These can interfere with spacecraft communications and navigation systems. In extreme cases, electromagnetic forces can induce currents in long conductors, a phenomenon already observed on Earth during major solar storms. On a broader scale, the solar system moves through the galaxy, and this motion exposes it to varying environments. As the Sun orbits the center of the Milky Way, it passes through regions with different densities of interstellar gas and dust. These changes can subtly influence the heliosphere, the protective bubble created by the solar wind. A compressed heliosphere could allow more cosmic radiation to penetrate the inner solar system, increasing radiation exposure for planets and spacecraft alike. Though these effects unfold slowly, they add another layer of long-term danger. Psychological and biological dangers must also be considered when discussing the solar system, especially in the context of human exploration. Isolation, confinement, and distance from Earth impose stresses that can be as dangerous as physical hazards. Long-duration missions expose astronauts to altered day-night cycles, limited social interaction, and constant risk, all of which can affect mental health and decision-making. A small mistake in such an environment can have fatal consequences, turning psychological strain into physical danger. Biological contamination presents a more subtle risk. As humans explore other worlds, there is a danger of contaminating them with Earth life or bringing back unknown biological agents. While the likelihood of encountering harmful extraterrestrial organisms appears low, the consequences are uncertain. Protecting both Earth and other worlds requires strict protocols, reminding us that danger can arise not only from nature, but from our own actions. Even success can create new dangers. As technology improves and space becomes more accessible, the number of objects operating in and traveling through the solar system increases. Each new mission adds complexity, traffic, and potential for interference. Navigating this increasingly crowded environment requires coordination and foresight. Without it, the risk of collisions and cascading failures grows. Throughout all these examples, a common theme emerges. Danger in the solar system is rarely isolated. It is interconnected, layered, and often cumulative. An asteroid impact is not just a collision, it is a geological, atmospheric, and biological event. A solar storm is not just an outburst of energy, it is a technological and societal challenge. Understanding danger means understanding systems, feedbacks, and thresholds. This systems perspective also reveals opportunities. By studying dangerous objects, scientists gain insight into planetary formation, evolution, and habitability. The same asteroids that threaten Earth carry records of the early solar system. The same radiation that damages electronics reveals the structure of magnetic fields. The same volcanic activity that creates hostile terrain may also create environments where life could exist elsewhere. In this way, danger becomes a teacher. It forces precision, humility, and cooperation. It encourages long-term thinking in a species often focused on the immediate. It connects disciplines from astronomy and physics to geology, biology, and engineering. Each dangerous object in the solar system is a reminder that knowledge is our most powerful tool. As humanity looks ahead, the question is not whether the solar system is dangerous. It clearly is. The question is how we choose to engage with that danger. Ignoring it leaves us vulnerable. Respecting and studying it empowers us. The history of life on Earth shows that survival favors those who adapt, anticipate, and learn. The solar system will continue to hurl rocks through space, unleash solar storms, and reshape worlds through forces far beyond human control. but it will also continue to offer opportunities for discovery and growth. By understanding the most dangerous objects within it, we gain not only the ability to protect ourselves, but a deeper appreciation of the dynamic, ever-changing environment that made our existence possible. In the vast darkness surrounding our planet, danger and wonder are inseparable. The same cosmos that threatens also inspires. To study the most dangerous objects in the solar system is to confront reality without illusion, to recognize our vulnerability without surrender, and to embrace knowledge as the bridge between fear and exploration. In doing so, we affirm that even in a universe filled with hazards, understanding remains humanity's greatest strength. In the broader perspective, what makes the solar system truly dangerous is not any single object, but the constant interaction between forces that never rest. Gravity pulls, radiation flows, surfaces fracture, and orbits evolve without regard for life or intention. The universe does not act with malice, yet its indifference can be just as deadly. Survival within such an environment depends entirely on awareness, adaptation, and foresight. As our technological reach extends farther from Earth, we step increasingly into regions where natural margins for error disappear. A minor malfunction near Earth may be survivable, but the same failure near Jupiter, the Sun, or deep space can be fatal. This reality reshapes how humanity must think about exploration. Courage alone is not enough. Precision, patience, and respect for cosmic forces become essential tools. The study of dangerous objects also reshapes our understanding of safety itself. Earth feels stable because we live within a brief window of calm. Geological layers, cratered surfaces on other worlds, and the scars of past impacts remind us that stability is temporary. The solar system has never been perfectly safe, and it never will be. What changes is our ability to predict and respond. In this sense, the most powerful defense against danger is a knowledge. Every asteroid tracked, every solar flare measured, every hostile environment explored reduces uncertainty. Uncertainty is the true enemy. When danger is unknown, it overwhelms. When it is understood, it becomes a problem to solve rather than a fate to accept. The solar system is not a fragile museum frozen in time. It is an active, evolving system shaped by energy and motion. Dangerous objects are not anomalies. They are fundamental components of how planetary systems work. Without them, worlds would not form, surfaces would not renew, and life itself might never have emerged. To understand the most dangerous objects in the solar system is therefore to understand the system as a whole. It is to recognize that destruction and creation are inseparable, that risk and opportunity travel together, and that humanity's future among the planets depends on learning how to navigate both. In facing these dangers with clarity rather than fear, we take another step toward becoming a truly spacefaring civilization.